Hello everyone, my name is Belén Hernández. I work at the Technological Center ITAINNOVA in Spain, and I am presenting this contribution entitled An in-house real-time friction reduction tool for optimizing the design of molds prior to the production. This work was developed within the European project MouldTex. Dynamic rubber seals are one of the main industrial applications of elastomers, and they are widely used in industries. Such components are a critical part of many rotating and sliding devices. For example, they are used in motors and hydraulic systems, and their primary function is to prevent leakage while they support millions of load cycles. Consequently, friction occurs between the sealed surfaces. And reducing friction is a constant challenge since it provokes heat generation, accelerates wear, and causes damage and premature leakage. Eventually, this situation implies an increase in the system power consumption, in the maintenance costs, and even catastrophic failure situations may occur. Within this background, MouldTex project emerges due to the need to look for industrial solutions that manage to reduce friction in dynamic rubber seals within the framework of a sustainable economy. The solution addressed in the project involves engraving microtexturing on certain surfaces of the seal with a sustainable laser-based methodology. Initially, it was proved that microtexturing is a potential technique for reducing friction, and it does not affect the functional properties of the component. However, we found in the project an outstanding side result. In particular, we found that under some circumstances, microtexturing can increase friction. At the same time, other implicit basic functions of the texture are identified. It allows traces of the wear to be trapped, it acts as a deposit for the lubricant, it improves the hydrodynamic pressure, and it involves reducing the contact area between surfaces so that there is a reduction in adhesion. Regarding the design, there is a need to adapt the pattern of each type of contact system and operating conditions, so one of the major challenges is to define how the microtexture should be. Of course, looking for the best design based on a trial and error would become an extremely slow and expensive process, so an advanced modeling software, which is called MouldTex Optimizer, is defined for optimal pattern identification for each specific application, resulting in significant friction reduction for dynamic rubber seals. Regarding the manufacturing process, micropatterns can be individually engraved by laser direct application in a separate post-process after seal manufacturing, but this approach is not feasible for current mass production. So the goals are to develop the potential of the microtexturing technique to reduce friction on dynamic rubber components and to implement a novel and cost-effective manufacturing technique on real production lines. In the project, it is postulated that the microtexture seals are manufactured by transferring the micropattern from the surface of the mold to the component. In other words, laser technology is applied directly to the surface of the mold, but only once, to create microprotrusions. Then they are transferred to the seal in the form of microcavities during the molding stage. The benefits of the technology are the improvement in friction by more than 20%, depending on the case, and decrease wear until at least double the lifetime of the component. Besides, both the performance and the efficiency of the processes will be improved. And economically, the investment costs will not be more than 10% compared to the conventional manufacturing. The workflow of the technology is summarized here. First, given a need of a client to optimize friction, the specifications of the particular application and the requirements have to be defined. Then, the advanced modeling software, the MouldTex Optimizer, is used. It consists on a simple web platform with user-friendly visualization techniques that provides results in real time regarding friction reduction and determines the optimum texture pattern to maximize friction reduction. Moreover, it is possible to analyze the feasibility of the demolding process. In the following slides, I will explain how it is built, and then I will demonstrate its functioning. After that, the mold is manufactured and the laser treatment is applied. Then the coating will be applied to the textured mold if necessary, and finally, the mass production process of rubber seals is executed while the quality control is assured. Regarding friction behavior, the software is based on a complex mixed friction model and experiments with real seals, which are simplified through reduced order modeling. In particular, reduced order modeling is a numerical method for multivariable problem simplification, which reduces dramatically the computational cost required for solving complex numerical models and synthesizing experimental data. Our approach aims at describing and hence predicting a system's behavior through a mathematical approximation by preserving its main characteristics and physical parameters. As a result, the simple platform allows the user to obtain real-time friction reduction prediction for a given set of parameters. In particular, the geometrical parameters that characterize the microcavities are the diameter, the distance, and the depth, and the parameters for the operational conditions are the pressure and the velocity. Moreover, an optimization algorithm is implemented to provide an optimum tailored texture pattern adapted for each type of contact system and operating conditions. On the other hand, the presence of microprotrusions in the mold may dificulty the demolding, so this process is analyzed experimentally and the knowledge is integrated into the tool. To that end, the experimental data are simplified again with reduced order modeling. In this case, the tool allows the user to analyze from a qualitative standpoint the demolding forces for specific texture patterns and to determine which is the most appropriate texture in terms of demolding forces. Now I'm continuing with a virtual tour to show the functioning of the MouldTex optimizer. And this is the main page of the tool, and it provides several menus. On the upper part of the screen, there is a navigation menu where the user can select the seal application, the rubber material and hardness, and the seal geometry. For example, let's take a translational application and a U-cap seal made of FKM 90A. The menu on the left is used to select the module to be visualized. In particular, modules are divided into friction reduction data and demolding forces, and as previously explained, they are constructed with the reduced order models that compile numerical and experimental data. Within both options, either friction reduction or demolding forces, the user can represent real-time visualization, real-time optimization, and the quality of the reduced order model. In terms of real-time visualization, the website allows visualizing the ROMs in different formats, such as 2D or 3D graphs, or only with numerical values. In the first option in the menu, which is the 2D graphs, the friction reduction is represented against a selected variable for specific values in the remaining parameters, which are selected from the right side sliders. If the user changes the values, the tool automatically updates the graph and it can be adjusted to the plot area. In this case, the depth is represented in the plot, so it is disabled on the right, while the rest of geometrical parameters that include the distances between dimples and their diameter can be varied. Additionally, the operational conditions of pressure and velocity can also be changed with the sliders. Let's say that the graph represents the depth on the x-axis by default, but the user can change which variable is represented from this drop-down menu. Well, next, 3D graphs can be visualized in the following option. In this case, the philosophy is the same, but here the friction reduction is represented against two variables, which of course can be selected from the drop-down menus. Regarding the sliders, the options represented in the graph are disabled and the user can change the value of the remaining ones. Additionally, it is possible to interact with the graph by rotating it, for example, and to select values from the surface response. Well, the section devoted to numerical values requests the user the selection of all parameters from the sliders, and the output reveals if the combination decreases or increases friction. The image on the right gives an idea of how many dimples fit in a representative area, and it changes as I change the geometrical parameters. The next option leads me to the real-time optimization. This feature allows visualizing the optimized target results in real time when input parameters are modified by the user. In particular, the output parameters are the ones describing the texture pattern, including the distance, the diameter, and the depth. Due to confidentiality reasons, the specific values for the output parameters are hidden behind the black boxes. Well, through this page, it is possible to optimize for any value of the input parameters and compare up to 4 operational scenarios at the same time. The goal is to find the optimal pattern for one operational scenario and see the effect on friction for the other 3 scenarios. For example, let's see what happens with 2 different scenarios where arbitrary combinations are selected. On the scenario on the left, I select 2 bars for the pressure, and for the velocity, 30 millimeters per second is selected. Then the second case on the right is defined by 1 bar pressure and a velocity equal to 10 millimeters per second. Well, the optimization tells us that if we optimize with respect to the first scenario, we will achieve a reduction in friction of 14.8%, while in the other scenario, we would be improving the friction by 3.1%. And here we would have obtained an optimum combination of texture. On the contrary, if we decide to optimize with respect to the second scenario, in the first case, we will improve by 12.1%, somewhat less than before, which was 14.8%. And in the situation on the right, we will reduce friction by 4.5% compared to the 3.1% that we had before. So in this case, we can see that in one way or another, we always have friction reduction, but we can see other scenarios. For example, if I change the circumstances of the second setting to 0.5 bar and 5 millimeters per second, we can observe that depending on the case for which I optimize the result, the friction can be reduced or increased. So the tool helps the designer to define the best solution. The next option is the raw quality module, which can be used to check if predicted values are in good agreement with the original data. And in an ideal situation, predicted values should lie on the red line. After concluding the friction reduction module, on the other hand, the module for the molding forces has the same structure and capabilities. And in this case, the optimization option determines which combination has the lowest demolding force for a given material. So the virtual tour of the easy-to-use and versatile MouldTex optimizer finishes here, and I reached the end of the presentation. So thank you for your attention. I would be pleased to answer your questions or to discuss any concern. And if you wish to complete a survey about the project and the software, please feel free to access to the link below. Thank you again.